Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello teacher, hello students. Welcome to today's lesson on the different types of proofs. In the last lesson, we learned how to test the validity of formal arguments. We learned how to use truth tables, and we also learned about the rules of inference. Today, we are going to learn the different types of mathematical proofs. Are you ready, students? Let us begin. We will start by defining what proof means in the field of mathematics. The proof of a given statement is a sequence of statements that form an argument. If a valid argument can be constructed in defense of a statement, that statement is proved. There are several different ways of proving statements. Today, we will study the most common methods. As an example of a proof, let us consider the statement that if n is odd, then n squared is odd. First, we assume the truth value of the premise, that n is in fact, an odd number. Then, we assume that n is equal to 2k plus 1, where k is an integer. It follows that 2k plus 1 squared is equal to 4k squared plus 4k plus 1. We can derive that equation making the expression 2 multiplied by 2k squared and 2k plus 1. This, in turn, is equal to 2m plus 1, where m equals 2k squared plus 2k, which is an integer. All this leads us to conclude that n squared is an odd number, as it is one more than an even integer. We have made a direct proof. It is the simplest in terms of concept, stating that if P is true, then Q must also be true. To construct a proof in this way, we must assume that P is true. Then we use the rules of inference along with facts that have already been proved to demonstrate that Q must be true as well. Another method we can use is called an indirect proof. As the name implies, this method proves the truth value of a statement by proving its contrapositive. In other words, if the statement, if P then Q is true, the statement, if not Q then not P, is true as well. A third method is called the method of cases, or the method of exhaustion. When we use this method, we must consider each and every possible case. For example, for the statement n squared plus 1 is odd for all integers, we would work through two cases to make a proof. The first case assumes that the statement that n squared plus 1 is odd is correct. The second case assumes that the statement is incorrect, that n squared plus 1 is even. It is time for an activity, students. Use the method of cases to prove that no square number ends in an 8.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. Were you able to make the proof using the method of cases? Since the final digit of any square number is determined by the final digit of its square root, we only have to look at single-digit numbers to use every possible case. Let us do this now. In looking at each of these cases, we see that no square number will ever end in an 8. Were those your answers? Well done. Now, let us try applying the indirect method. Prove that there are no positive integer solutions to the equation x squared minus y squared equals 1.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
First, we must assume that there is a solution where both x and y are positive integers. If this is the case, we can factor this equation into x minus y times x plus y equals 1. Since x and y are integers, we can write that x minus y equals 1 and x plus y equals 1 because 1 times 1 equals 1. We can also write that x minus y equals negative 1 and x plus y equals negative 1 because negative 1 times negative 1 also equals 1. In the first case, we can use substitution to solve for x and y. Now we can substitute x into the equation. Then we can substitute y equals 0 into the equation. Therefore, the first case gives us x equals 1 and y equals 0, which contradicts our assumption that x and y are both positive. In the second case, we can use substitution to solve for x and y. We substitute x into x plus y equals negative 1. Then substitute y into the equation. Therefore, the second case gives us x equals negative 1 and y equals 0, which also contradicts our assumption. In conclusion, we can state that there are no positive integer solutions to the equation x squared minus y squared equals 1. There are two more methods we will study today, students. The next is called proof by contradiction. To prove that a given statement is true, using proof by contradiction, we must follow these steps. First, we assume that its negation is true. If, through a number of steps, we arrive at wrong conclusion, this leads us that our assumption was not correct. This in turn shows that the given statement is true. That will be the proof. The last method we will learn today is called the proof by counterexample. Using this method, we must find a state in which the premise does not infer the conclusion. For instance, to disprove the statement, every odd integer n under 10 is prime, we must be able to produce a counterexample. the number 9 is a counterexample. It satisfies every aspect of the premise, but not the conclusion. Note that just one counterexample is enough to disprove a statement. Let us test what we have learned. Prove that the sum of two n even numbers is even where n is greater than 0 using proof by contradiction.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again. We first must assume that the sum of even integers is odd. This means that 2 plus 4 plus 6 and so on plus 2n is an odd number. We can factor out a 2 for this equation, giving us 2 times the sum of 1 plus 2 plus 3 plus 4 and so on plus n equals an odd number. Stated another way, 2 times n over 2 times n plus 1, which is an odd number, using our formula for the sum of arithmetic progressions. In this equation, we have n over 2 times n plus 1, which is an odd number. This is a contradiction because n times n plus 1 is always an even number. Therefore, our statement that the sum of 2n even numbers is even has been proved by using an indirect proof. Today, we have learned about different types of mathematical proofs. Remember, since many mathematical statements are implications, the techniques for proving implications are important. Recall that the implication, if P then Q, is true unless P is true and Q is false. So we notice that when the statement is proved, the only thing to be shown is that Q is true if P is true. It is not usually the case that Q is proved to be true in isolation. That is all for today. In our next lesson, we will learn more about the different applications of mathematical proofs. Until next time, thank you, teacher. Thank you, students.